My name is Bo. I'm also a co-founder at Polymer. Thank you everyone for coming to the inaugural IBC Summit. I wanted to introduce Polymer Labs first. We're working on accelerating IBC adoption by building an IBC transport hub. Some background on myself. I am a technical lead here. My previous experience is working on infrastructure at Chronosphere, Uber, and Capsule 8. We're going to talk about the history of IBC, speak on IBC's potential as a universal interoperability standard, and also talk about how Polymer will expand IBC to Ethereum and beyond. So IBC has a rich history that some folks are not aware of, or many folks are not aware of. In fact, IBC was originally conceptualized way back in 2016. Jae Kwon wrote the initial specification for it in the Cosmos white paper. In 2017, Ethan Frey created the first working prototype and specifications for IBC. In 2019, Chris Goes and the Goric team worked on the current iteration of the IBC specifications and implementation. In 2020, Aditya, Colin, Federico, and a number of other builders joined to work on taking IBC to production. And in 2021, we had the first IBC transaction in production. In 2022, we have ongoing work on the application side of IBC in the form of interchain accounts, relay incentives, finalized middleware, and more. So IBC's future includes many important innovations. We have increasing client diversity. The client definition for IBC allows for a lot of flexibility in the definition of how you build and how you define clients. We have a focus on upgradability, a focus on incentivization, a focus on developer UX and user UX with path unwinding. We have a focus on flexibility and scalability with multi-hop. And we have a focus on security as well. So I want to say that IBC was conceived of from the beginning as a universal interop standard. Alternative interop protocols are being built as products, which are value extracting and also drive ecosystem fragmentation. We end up in a world where chains speak different languages. We have multiple translation layers, which create a vendor lock-in problem and cause value extraction, and also divides the network topology up further. I wanted to zoom in on the vendor lock-in problem and value extraction in some of these alternative interop protocols. So if we think about the web, and we want to imagine a world where Verizon could look at the data being sent over the wire and price those data packets. So imagine Verizon could say, hey, I just saw that you did a bank transfer. Maybe it was via Venmo, maybe it's via some other application. You sent $10,000 to a friend. Maybe the app takes a fee. Verizon sees that you're doing this transaction. Verizon says, wait, I'm not going to send this transaction. I want a fee. I'm going to take 1% of that Venmo transaction. Do we want the infrastructure layer to peer into the application layer and price those data packets and restrict those data packets and come in and extract value from them? I think we can do better. So there are multiple characteristics of IBC that are ideal for broad adoption. We have a modular design. If we think about Cosmos SDK, from the beginning, Cosmos SDK was likely one of the first blockchain frameworks that was designed with modularity in mind. IBC is split up into multiple layers, which we'll discuss later, and we'll show why this modular design allows for different types of applications to be built on top. There were formal specifications from the beginning. These are very important when you want to have decentralized innovation. If everyone cannot agree on what to build and what are the interfaces to build on, it's very difficult to collaborate. You have an expressive transport layer standard that's also not value extracting. It allows any number of applications to be built on top, ranging from infrastructure protocols, which infrastructure developers can work on, to application protocols, which application developers can work on as well. There's security and decentralization as first-class citizens, permissionless adoption. This means that any network that implements the IBC protocol can speak to any other network in any other chain in the IBC network with no middleman. It's also minimally value extracting, which means that the IBC transport layer cannot peer into the application layer and extract value from that. Despite the advantages of IBC, there are obstacles to broader adoption, which we're trying to solve here at Polymer. One of the primary challenges is that native integrations are resource intensive and time intensive. There are a number of initiatives to bring IBC, a native integration of IBC into different ecosystems, to Polkadot, to Avalanche, and other networks as well. We have seen that these take time, these take resources, it's challenging. Polymer Transport Hub allows for easy IBC adoption and integration. IBC also has strict compatibility requirements. If we look at the formal specifications or the core specifications of IBC, we can see that it's very opinionated on how you should compose data, how you should commit to data, and so on. These strict compatibility requirements also make it difficult and challenging, and in some cases impossible to integrate IBC into certain chains. Polymer decouples the application layer of IBC from the transport layer of IBC, making the boundary asynchronous and allowing for us to more easily integrate IBC into these different chains. There's also poor performance on various chains. For example, verifying consensus on a chain like Ethereum can be quite expensive. Additionally, verifying proofs can also be very expensive as well for the data that you have committed on a different chain. Polymer attempts to make this process more scalable and more performant by being an adaptive middle hop in the IBC network. So we're going to talk about how Polymer brings IBC beyond the cosmos. This part's somewhat more technical, so for the non-technical folks in the audience, I apologize. It might be painful, but pain is good. So reviewing the interoperability model, first we have 3 layers. We have the application layer, transport layer, and state layer. The state layer in the OSI model for the centralized web, we have physical network links at this layer, TCP/IP at this layer, and HTTP at this layer. And on the other side, we have the interoperability model for the decentralized web. We have the state layer, which has, translates to IBC connections and light clients. We have the transport layer, which translates to IBC channels. And we have the application layer, which translates to IBC interchain accounts and other IBC standards. So what does IBC look like today? At the application layer of IBC, we have IBC app implementations of IBC application specifications. IBC applications talk to each other using IBC channels, as you can see here. We have a transport implementation, the canonical one being IBC Go. Packets are routed between this layer, from chain A to chain B, over this layer. And we have light clients at the state layer of IBC, which connections are built on top. Technically, this is not a perfect analogy. Technically, these 3 abstractions all live at this layer, but just to kind of motivate what's going on underneath the hood. So how do we extend IBC beyond the cosmos? As you can see here, we have a few boxes, a few question marks. And referring back to the earlier slide on what makes integrating IBC difficult, we can see that transport layer has strict compatibility requirements, making it somewhat difficult, challenging, and also time-intensive to integrate. At the light client layer, verifying consensus can be expensive, another question mark. And on the IBC chain, there's a problem of how do you verify the consensus of this IBC incompatible chain. So to motivate where Polymer sits in the stack, we now shift the focus over to multi-hop IBC. This is what a multi-hop IBC setup looks like with Polymer in the middle. Once again, we have 2 applications talking to each other with Polymer as a middle hop. You can establish a channel between application on chain A and an application on chain B over 2 connections, one being a connection between chain A and Polymer, and another being a connection between Polymer and chain B, and you can have data flow over this. But what does this look like internally? Well, going back to what I said earlier about Polymer decoupling the application and transport layer of IBC, we can see that chain A now becomes what we call a virtual chain, and transport has now become decoupled from chain A to Polymer. Now we have a virtual transport layer on chain A that can route packets across to Polymer, and now data can flow across chain A and chain B seamlessly through an easy integration via Polymer in the middle. So what's Polymer's technical mission? First and foremost, we want to enable mass IBC adoption. The faster we can do integrations, the more adoption IBC will see. We want to build an IBC transport hub to bring the IBC transport layer to all connected chains. And this is very important. We also want to make IBC adaptive and performant across heterogeneous chains. This is less of an issue in the current IBC topology because the IBC network topology is currently homogeneous. We also want to think about the IBC hub and also the network as a client or state layer marketplace. It's challenging to build clients for different chains, and we want to incentivize builders and collaborate with builders across different ecosystems to encourage them to further IBC adoption. So IBC is the future of decentralized interoperability. We have a diverse and capable community of builders and users. We have decentralized innovation and adoption across many ecosystems. And we have a protocol designed from first principles with fundamental crypto values. IBC as a universal interoperability standard, yeah, we're obsessed with it.